video, okay? I'm gonna try to do a video, a quick one. All right, guys, in chapter 17, we're going to be talking about aqueous equilibrium. Specifically, in this chapter, we're going to be talking about buffer solutions at the beginning. Among those buffer solutions, we're going to talk about what they are and how to calculate the pH of those buffer solutions. Also, how to calculate the changes that occur upon addition of an acid or a base to those buffers. After that, we're going to be moving to the second topic, which is going to be titrations. These are the goals that I encourage you guys to read separately. I've put one in red here because this one, we're not going to be doing the calculations fully due to time constraints because of the week that we lost. But we will be talking about what substances are present at any given point within that titration. So I do want you to know that even though we're not going through the calculations, I do want you to be able to identify what molecules are present along the titration in this particular case. All right, so having said that, let's go ahead and get started. Introduction to buffers, which is section 17.1 of your online book. And to begin with, what is a buffer? So a buffer is a solution that resists the change in pH whenever a small amount of an acid, strong acid or strong base is added to it. So obviously these kind of solutions, buffer solutions, are hugely important in a number of fields. They're actually critical to our lives. For example, our blood and our physiological fluids required to be maintained at a certain pH, otherwise everything would fall apart, right? Our proteins would not be stable, they would denature, those physiological processes would not work if we had the pH vary. So our bodies utilize a number of natural buffer systems to be able to maintain the pH within a certain range. Similarly, whenever we're doing chemistry, we need to maintain the pH to enable control over reaction processes. And I'll tell you, in my particular field where we do cancer nanomedicine research, we actually utilize buffers to be able to maintain the pH of our cells. We have cells that we utilize for studies of anti-cancer effect, and to maintain those cells alive and thriving, we need to maintain them within a certain pH level that represents the pH level that they would be in a natural environment. So it is a hugely important field for those of you who are in chemistry, biochemistry, biology, any kind of health-related career would also benefit from knowing about buffers. All right, so how do these buffers actually work? Basically, you're going to have a solution that is going to contain certain components that are going to be neutralizing whatever acid or base is added to the system. So they need to be able to react with and neutralize that acid or base. The mechanism for neutralization is based on the equilibrium of a weak acid and its conjugate base, and they are governed by this common ion effect, which we're going to be talking about in the next few slides. All right, so common ion effect. So let's say that we have a solution of acetic acid, okay? So we're starting with a solution of acetic acid, and to that solution, we're going to be adding sodium acetate. So we understand that acetic acid is a weak acid, and because it is a weak acid, when it is placed into an aqueous environment, it will be partially dissociating into the hydrogen ion and the respective anion, which is the acetate ion. This is an equilibrium process, meaning that all three substances are present at any given point, and the ratio of them has to do with the Ka of that process. All right, so now to that equilibrium, we add sodium acetate, which is written down here. So sodium acetate is a salt. Specifically, it is a soluble salt. And so when you place that salt into that same solution, which is an aqueous solution, that salt is going to completely dissociate into the sodium ions and the leftover anion, which is CH3COO minus, or the acetate ion. And now you can see that all of a sudden we have basically the same ion, this common ion. And this is what we're talking about. What happens when we add a substance that shares an ion with the ion that was already participating in an equilibrium process? So I want you guys to think about Le Chatelier's principle in this case. Remember that whenever we had an equilibrium, we talked about what would be the effect of adding some of the reactant or adding some of the product, which direction that would shift the equilibrium in, and what effect would that have on the concentrations of the reactants and products. So in this particular case, again, this is our equilibrium, the acetic acid equilibrium with acetate and hydrogen ions. To that, we said that we're adding this substance, which what we really care about is the fact that we're adding acetate ions. So what happens to the equilibrium if we add acetate ions? Acetate ions are one of our products. And because we are increasing the amount of the products, that basically is going to cause a shift in the equilibrium toward the left-hand side of the reaction. So that's basically answering our first question. In which direction does the acid dissociation equilibrium shift? Toward the left. Second question is, what happens to the percent dissociation of the acid whenever that shift occurs? So, all right, let's think about that. So in this particular case, we said that there's a shift toward the left-hand side, but we're being asked about dissociation. So the dissociation of the acid means the reaction of that acid going to the right. So if we're saying that there's a shift toward the left, that means that most of the acid or more of the acid is going to be maintained in the associated or neutral form as opposed to being dissociated. So the overall effect in terms of the percent dissociation is that it actually decreases. Ooh, and I'm having a hard time writing. Sorry about that. Give me 1 second while I try to get my act together here. Okay, so the overall effect is that the percent dissociation is going to decrease. All right, what happens to the pH of the solution? Well, we already said that we have, We already said that we have a shift toward the left. A shift toward the left means that the concentrations of the products are actually going to decrease, and instead the concentration of the reactants is going to increase. So because the hydrogen ion concentration is going to decrease, that basically is going to lead to a decrease in the acidity of the solution. So I'm going to write it like this: the acidity is going to decrease. And if the acidity decreases, then what happens to the pH is that it increases. Because remember that a pH that was less than 7 was an acidic pH, while a pH that was bigger than that, greater than 7, was basic. So as we decrease the acidity, we're also increasing the pH. So the answer here is, what happens to the pH? It actually increases. Now, what ions behave as spectator ions in this whole process? The sodium ion right here, which came into the solution with the salt, it actually has no effect on the equilibrium because it is not part of the equilibrium. So that sodium ion is what we're going to be calling our spectator ion. Okay. All right, so how do we define this common ion effect? Basically, whenever we have a weak electrolyte, which is combined with a strong electrolyte that contains a common ion, the ionization of the weak electrolyte is suppressed. So just to break this down, a weak electrolyte in this case is going to be your weak acid or your weak base, if that's what you have. And then that weak electrolyte, which is undergoing an equilibrium, is put together with a strong electrolyte, which that strong electrolyte could potentially be a salt, as in the example that we just had. And if that salt contains a common ion with the weak electrolyte, then the ionization of the weak electrolyte is suppressed, meaning that there's going to be a shift in the equilibrium toward the left, decreasing the extent of ionization or dissociation. So for the case of the equilibrium of a weak acid, the common ion is going to suppress the formation of hydrogen ions, rendering the buffer solution less acidic and thereby increasing the pH relative to that of the pure weak acid. All right, so question. What effect would addition of ammonium chloride have on the following equilibrium? So we have an equilibrium process of ammonia in water. The ammonia is a weak base and therefore is going to be accepting a proton to form the ammonium ion. And in that process, the water donates the proton, now becoming hydroxide ion. So the question is, what effect is this strong electrolyte, this salt, going to have on this equilibrium? So of course, we can immediately see that the ion, the common ion that we have here is the ammonium ion, right? Ammonium is part of the equilibrium. It is one of the products. So whenever we come and add that ammonium chloride, which completely dissociates into ammonium ions and chloride ions, the ammonium is basically effectively increasing the amount of ammonium that we have and thereby causing a shift toward the left. So now we can look at our answer choices and see which one is the correct one. All right, so basically the first one says the equilibrium would shift toward the right. So we can go ahead and remove that as an option. Similarly, we can remove number 2 as an option because of that. All right, number 3 says the equilibrium would shift toward the left. That's true, leading to a solution of higher pH, while the next one says leading to a solution of lower pH. So let's think about the pH effect. In this case, we said that there's a shift toward the left. A shift toward the left means that the concentrations of our products are going to decrease and the concentrations of the reactants are going to increase. So if we are saying that the concentration of hydroxide ions is going to be decreasing, that means that the solution is becoming less basic. And a solution that is less basic, which is the same thing as being more acidic, would actually have a lower pH. So lower pH, that means that our answer is number 4. Okay, so now that we have talked about the effect of a common ion on an equilibrium, what we're going to do is to learn how to calculate the pH of a solution that has been affected by this common ion effect. To do that, we're going to identify the strong and the weak electrolytes. The strong electrolyte is going to be the salt that brings in that common ion, and the weak electrolyte is going to be either your weak acid or weak base, depending on the problem, which are undergoing an equilibrium. We're then going to set up an equilibrium dissociation reaction for that weak electrolyte, and we're going to use that process to set up an ice chart. So for example, let's say that we were dealing with a weak acid. We would set it up as HA in equilibrium with the dissociation products, which are H plus and A minus. Or if we had a base, let's say ammonia, a weak base, then we would set it up by reacting it with water. The base would act as a proton acceptor, becoming NH4 plus, and the water would be the proton donor, liberating or forming hydroxide ion. Now, again, we're going to utilize this to set up an ice chart. And in that ice chart, we would start by putting our initial concentration of the weak acid or the weak base. So for example, let's say that we had 0.1 molar of the weak acid, then we would put that number here. Similarly, let's say that we had a 0.1 molar of the ammonia. These are two independent problems just to show you the setup for whenever you have a weak acid versus a weak base. All right, so the next part is that we're going to be putting the common ion from the strong electrolyte to be the initial concentration of the ion in the ice chart. What that means is that remember that the common ion is going to be this guy right here, the ion that is coming from the weak acid, or this ion that is coming from the weak base, which is also shared by the salt or the strong electrolyte that you are adding to that solution. So now instead of putting 0 for these guys right here, what we're going to use is to utilize the concentration of that salt to find a number to put here for the initial concentration of that common ion. How do we find that number? So basically that number would be the molarity of, the molarity of those ions is going to be equal to the compound molarity times the subscript. What that means is let's say that for this guy, I had a salt that was sodium A, where A is the anion, whatever that anion is. So here, my subscript for the A, it's a 1. And if I had a 0.1 molar solution of that, then the molarity of the A minus would have been exactly the same number because the subscript is a 1. So they are on a 1-to-1 ratio. On the other hand, let's say that for this guy, my salt was something like an ammonium. Let me erase that. Let's type it a little bit better. NH4 2SO4. So let's say that we had ammonium sulfate. The common ion is ammonium ion, right? But now I have a subscript of 2. Then if my compound is 0.1 molar, then the amount of ammonium ions that I actually have, the concentration of it, is actually twice that because of the ratio. So this would be actually 0.2 molar. So that's what I mean by taking the compound molarity and multiplying it by 2. We're going to be ignoring the spectator ions, which in this case would have been the sodium ion, and in this particular case it would be the sulfate ion, and I'm sorry that I am out of space, SO4. I'm out of space for this guy. But the sulfate is basically the spectator ion. All right, so basically, again, what we're going to do is that we're going to come and utilize that number here for the initial of the ion. So for these particular examples that I utilized in this page, the initial concentration of this anion would have been 0.1 for the A minus from here. And then for the ammonium, it would have been 0.2 here. And basically, that's the only difference. From there, you would continue to put your, whatever other information you might have. You would then do your changes by utilizing the X, and then you would set up your equilibrium line. And finally, utilize the K equations, either Ka for this, for the weak acid equilibrium, or a Kb for the weak base equilibrium, and find what the value of X would have been. We will do a problem in the next slide. All right, so the first example that we're going to be doing is calculating the pH of just a weak acid. And then we're going to do the exact same problem, but it's going to be the pH of a weak acid to which we have added a salt that contains a common ion, so that you can see the differences in how to approach the problem and the differences in the results. As we expect already, we know that the common ion is going to result in a suppression of the dissociation. And because of that, the concentration of that hydrogen ion in the end is going to be lower than expected. So, all right, let's get started. So calculate the pH and the percent ionization, which remember, that's the same thing as the percent dissociation, of a solution that contains 0.085 molar nitrous acid, HNO2, and we're given the Ka of it. Of course, we need to identify immediately that we're dealing with a weak acid, nitrous acid or HNO2, it's a weak acid. And of course, also if you are given a Ka, that also means that you have a weak electrolyte. A strong electrolyte, you would not have been given a Ka because there would be no equilibrium to consider. Anyways, since it is a weak acid, to find the pH of a weak acid, we always utilize an ice chart. And basically that ice chart is set up by looking at the dissociation of that acid. So we take the HNO2, we dissociate it into hydrogen ions and the respective anion, which is the nitrous ion. From there, we start with our initial. In this case, we have 0.085 molar concentration, so that is placed there. And initially, we have 0 and 0 of our products, the dissociation products. We then use negative X for the change for the nitrous acid. And then for the products, we're going to have positive X and positive X. We then add up all of the columns. So here we end up with 0.085 minus X. 0 plus x is x and 0 plus x is x. And what we're going to do now is that from that ice chart, we're going to set up a Ka expression to be able to relate the Ka to the equilibrium concentrations of our reactants and products. Utilizing that Ka expression, we're going to solve for x, and since according to our ice chart, x represents the hydrogen ion concentration at equilibrium, then we know that once we have that x, then we can go ahead and calculate the pH by taking the negative log of that hydrogen ion concentration at equilibrium. Once we have that, we can also find the percent dissociation, which is the same thing as the percent ionization, by taking the concentration of hydrogen ion at equilibrium and dividing it by the starting concentration of our acid and multiplying by 100 to make it into a percentage. So that's the pathway that we're going to take. You can see the process in the next slide. We set up the Ka expression by taking our products, x and x, which makes it x squared, divided by the concentration of the reactants, which is in this case 0.085 minus x. We then look at the value of the Ka and notice that the Ka is 4.5 times 10 to the negative 4. So that's a very small Ka, which tells us that the dissociation is not going to go forward toward the products to a very large extent. And because of that, we can assume that X is very small. Remember that whenever we make that assumption, we basically are going to be neglecting the amount of X that is being either added or subtracted. So in this case, I can go ahead and assume that this X that is being subtracted from the initial concentration is very small. And so because of that, my math basically simplifies to x squared divided by 0.085, and that's equal to Ka. From there, I can then solve for x squared, which is going to be equal to 4.5 times 10 to the minus 4 times 0.085. And then I take the square root of both sides and find my value of x. So the value of x, as we said, is equal to the hydrogen concentration at equilibrium. And so we have basically found that one piece of information that now allows us to calculate the pH by taking the negative log of that concentration and getting our pH value. And finally, finding the percent dissociation by taking that hydrogen ion concentration at equilibrium, dividing it by the starting concentration of the acid and multiplying by 100 in order to get the percent dissociation. Of course, we always want to do kind of a reality check. Remember that this is a weak acid, and so we expect to have an acidic pH. So that checks out. All right, so now we're going to go to the next part of the problem, in which we are actually going to take the same acid at the same concentration, but this time we're going to have not just the acid, but in addition to that, we're also going to have a specific concentration of a salt that shares a common ion with that weak acid. And our job is to find the pH and the percent ionization again and see what are the effects that it has on those values. All right, so again, we're going to be setting up our equation for the dissociation of the acid. We start with the initial concentration of that nitrous acid, and what's going to be different this time is that we're going to have an initial concentration for that nitrite ion. We can see that the concentration of the potassium nitrite is 0.1 molar, and we can also see that the subscript for that nitrite ion is a 1, right? We have one potassium ion, one nitrite ion. Therefore, the concentration of the nitrite ion is going to be 0.1. And I want to make sure that I'm going to write that write that dissociation right here for you guys. So KNO2 dissociates into one potassium ion and one nitrite ion. That's a negative, sorry. And the ratio is a 1-to-1, right? So we don't have to multiply by 2. This little 2 is part of the nitrite, so it's not a subscript outside of that ion. So I just want to make sure that you understand that. All right, so now that we have the concentration of our initial ion, common ion, then everything else from there is the same, in that we're going to do our changes, which for the reactants are negative X, for the products are going to be positive X, and then we add our column, so 0.085 minus X for the reactant, and then for our products, 0 plus X, which is X for hydrogen ion, and in this case, we're going to have 0.1 plus X, which is different from last time. We're then going to set up, we're going to continue the same process that we did last time, which is to utilize our Ka expression to find X. Once we find X, we know that X represents the hydrogen ion concentration, which is exactly what we need to be able to find the pH and the percent dissociation. So that's what we're going to do. As you can see here, we set up our Ka expression, which is equal to our product concentrations X times 0.1 plus X, and that's exactly what we have, divided by the reactant concentration, which is 0.085 minus X at equilibrium. And all of that is equal to 4.5 times 10 to the negative 4, which is the value of Ka that was given to us. We are then going to assume that X is very small because of the fact that the Ka is quite small as well. And again, what that means is that we're going to be basically neglecting the effect of any X that is being added or subtracted from a starting concentration. In this case, we can make that assumption for both of these X's. And so that simplifies our math to now be just X times 0.01 divided by 0.085, which is equal to 4.5 times 10 to the negative 4. We then multiply both sides by 0.085 and divide both sides by 0.1, and we get our value of X, which is 3.8 times 10 to the negative 4 molar. And now we know that to calculate the pH, we're basically going to be taking the negative log of that concentration, of that hydrogen ion concentration at equilibrium, and we get our new answer, which is 3.42. And similarly, we're going to calculate the percent dissociation, which is equal to the hydrogen ion concentration at equilibrium divided by the concentration of the acid at the beginning of the problem, and times 100 in order to make it a percentage. And what I want you guys to see right now is the fact that the values have changed significantly. The pH before, in the absence of the common ion effect, was at 2.2, while now we have a 3.42. So as we expected, the overall dissociation of the acid was suppressed, and therefore we had a lower hydrogen ion concentration, which leads to a higher pH, because lower hydrogen ion concentration means that we have a less acidic system, and therefore the pH is going to be higher. So I wanted to make sure that you guys saw that. This slide actually compares the results of the two problems, just for you to be able to see them next to each other. Again, as I mentioned, the pH going from the acid-only problem to now having the acid in the presence of a common ion. The pH, oops, sorry about this. I just noticed that this says 4.42, but in fact it is a 3.42, as we just calculated. Okay. That makes more sense. So again, the pH increases because we have suppressed the dissociation of the acid. One other thing that we see is that actually the percent ionization of that acid goes down as we expect. Again, the percent ionization is the same thing as the percent dissociation. So everything checks out as we expected. And just to reiterate, the effect of a common ion is that whenever a weak electrolyte, such as a weak acid or weak base, and a strong electrolyte containing a common ion are together in solution, the ionization of the weak electrolyte will be suppressed, and therefore the percent ionization or percent dissociation is going to decrease. And that's something that I want you guys to remember well. All right, so as we said, the common ion effect is going to have an effect on the mechanism by which buffers work. And just to recap, a buffer is a solution that has the ability to resist change in pH after addition of small amounts of acid or base to it. And they do so by neutralizing the added acid or base. Now, in order for a solution to be called a buffer, there are a couple of requirements. The first requirement is that that buffer solution has to have both an acidic species, and when I say acidic species, I mean an acidic component that has the role of neutralizing the hydroxide ions from the strong acid that is added to it. And it also has to have a basic component or basic species in order to be able to neutralize the hydrogen ions from the acid that is added. So we have to have both acidic and basic species. That's the first requirement. The second requirement is that the acidic and the basic component of that buffer cannot consume one another, because if they consumed one another, then obviously they would not be available to neutralize any external acid or base that gets added to that solution. And so because of that, we have to be very careful with the selection of the acid and the base that we utilize. And specifically, what we're going to be able to use to make a buffer is to use a conjugate acid-base pair, because they will not be able to consume one another. So we're going to select either a weak acid and its conjugate base, or we're going to select a weak base and its conjugate acid. For example, here we have, this is acetic acid. I could have written it also as CH3COOH. But that weak acid is basically part of our buffer. Now, I need its conjugate base. As we know, the conjugate base of acetic acid, which would have been C2H3O2 negative, because it has donated a proton. Now, I cannot go and buy or find this acetate ion from anywhere by itself like this. You cannot buy or you cannot store ions by themselves. They always have to have a counter ion to make them into a neutral salt. So what I can use is a salt that contains that conjugate base. And that salt could be something like a sodium salt of that base. So notice that what I have listed here is the conjugate base in the form of a salt, and we're going to be talking about what types of salts would be suitable for the preparation of these buffers. Similarly, here we have a weak base such as ammonia, and what I need is to have its conjugate. This is a weak base, so its conjugate acid is going to have one extra hydrogen ion. Therefore, it's going to be NH4+. But again, I cannot buy or find a bottle of ammonium ions. What I can find is a salt that contains those ammonium ions. And in this particular case, I'm listing ammonium chloride as a source of that conjugate acid. So my buffer would be made from that weak acid or base and the conjugate in the form of a salt. All right, so how do these buffers work? Where we already said that the buffer is going to contain two components, an acid and a base, specifically a weak acid and its conjugate base, or a weak base and its conjugate acid. And we said that the role of those buffer components is going to be to neutralize any acid or base that gets added. So let's look at here at the center. What we have is our initial buffer components. We have an acidic component and a basic component. For this particular buffer, what we have is HF, hydrofluoric acid, and fluoride ions. So obviously the hydrofluoric acid is going to be my acidic component. Acidic. And this guy, it's its conjugate base, so this is my basic component. And now what we have to think is, what happens if I add acid to that buffer? So adding acid would be represented by this. Let's say that I'm adding HCl, which is a strong acid. Out of that HCl, the active component is going to be the hydrogen ion. So this is why I'm showing adding H+. That means that I'm adding a strong acid to the solution. All right, so we said that that acid is going to have to react with one of these two components in order to be neutralized. If I'm adding acid, the only thing that would make sense is for that acid to react with the basic component of my buffer. And that's what you see down here specifically. The H plus that came from that external acid that I added is going to be reacting with the basic component of my buffer, and the product of that reaction is going to be the formation of more HF. And if you notice, the product and what I'm using, they're both part of my buffers. So effectively, what I end up doing is that I end up increasing the amount of one of my buffer components by utilizing the other buffer component. And overall, neither of their concentration changes too much. But effectively, also what I have done is that I have completely removed or completely neutralized that acid that I have added, right? So that's the overall role of the buffer. Similarly, what happens if I add base? Let's say that I added sodium hydroxide, a strong base. Out of that strong base, the part that matters, or the part that is active in its basic function, is the hydroxide ion. And that hydroxide ion is going to be acting with the acidic component of the buffer, right? Because base reacts with acid. And so that's what you see here. The base that we added ended up reacting with the acidic portion of my buffer. And the products of that are going to be water, because the base acts as a proton acceptor forming water, and what's left is the fluoride. And again, just to have you notice, the product is also basically changing the concentration of the buffer components. And in this particular plot, the concentrations are shown by these bar graphs basically. Initially, I started with more or less the same concentration of my two buffer components. After addition of acid or base, the concentrations of the buffer components have changed a little bit. One of them goes up, the other one goes down. But effectively, you have neutralized or used up all of the acid or all of the base that you had. And just to reiterate again, if you're adding acid, that acid is going to react with the basic portion of your buffer, right, with the conjugate base. And if you're adding base, that base is going to react with the acidic portion of your buffer. In this case, that would be the weak base. The weak acid. All right, so here we're going to try to learn how to select a set of components to prepare a buffer. And this is a really important problem that I highly encourage you guys to make sure that you understand. This is critical for any of you who are going to be going into biology, biochemistry, or chemistry, because you will have to prepare buffers in later classes and in your career as well. And so this is something that is important for you to actually learn and understand and be able to do later on outside of this class. All right, so let's say that we want to prepare a buffer using acetic acid. What is the conjugate base of acetic acid? So, all right, we know that acetic acid is CH3COOH. So if we need a buffer, we need a conjugate base of that acid, and that would be CH3COO-. Basically, we have lost, or we have donated, the acidic proton. All right, can I find this in this way? Well, no, we already said that we cannot buy or store or obtain ions by themselves. But what we can do is to find a source of that ion in the form of a salt. And so how would you supply this conjugate? It would be in the form of a salt. Typically a sodium or potassium salt would work. And so let's go ahead and write sodium acetate would be a choice for this purpose. So my buffer overall would be made from acetic acid and sodium acetate. We'll get back to another problem that is similar to this, where we're actually going to be calculating the molar quantities or ratios, molar ratios of the substances that we need in order to get a buffer of a specific pH. All right, so what kind of salts can we use for selection in the preparation of a buffer? So we usually are going to use salts that contain the conjugate acid or base paired with a highly soluble counter ion. So because of that, we have to remember solubility rules a little bit. For example, if we need conjugate bases of weak acids, then we can use salts that contain sodium or potassium salts because according to the solubility rules, salts that contain group 1 metal ions are going to be soluble with no exceptions. So I can utilize any kind of salt that contains a group 1 or group 2, a group 1 metal ion, and sodium and potassium are going to be the salts that are most widely available. So like in the previous problem, we selected sodium acetate as a choice. We could also have used a potassium acetate as a choice for a buffer that contains acetic acid. Now, if I need a conjugate acid of a weak base, then what you would select would typically be a nitrate or chloride salt. Remember that nitrate containing salts are soluble with no exceptions. Chloride salts are mostly soluble. So for example, I could have something like ammonium chloride or ammonium nitrate because the chloride and the nitrate make those salts soluble. Of course, as a separate note, ammonium salts are also all soluble with no exceptions, but that's aside the fact here. All right, so question for you guys. Which of the following mixtures is a buffer? Go ahead and stop the video, give it a try, and come back to it when you are done. All right, so remember that a buffer is going to be made by taking a weak acid and its conjugate base in the form of a salt, or a weak base and its conjugate acid in the form of a salt. So we can begin by removing some that are not going to work for us. So for example, this guy right here, this is a strong base. Strong bases are not going to help me at all. This one right here is a strong acid, so I can go ahead and remove it. Same thing, same thing, same thing. Oops. So therefore, I have only one choice, but let's make sure that that choice is valid. So again, I need a weak acid, which phosphoric acid is a weak acid, and I need its conjugate. Its conjugate is going to be after it donates one proton, so H2 PO4 with a -1 charge. Again, I cannot just get an ion, so what I'm going to need is a salt that contains this ion. And we previously mentioned that typically salts of anions that contain potassium or a sodium counterion would be suitable, would be readily available for us to use. And that's exactly what we have here. So the answer choice is E. Of course, to be able to answer these kinds of problems, you have to make sure that you remember your list of strong acids and strong bases. That is going to be critical here. If you don't know that, you're going to miss this kind of problems that are actually quite easy. All right, let's move on to the next slide. So next clicker question, which of the following will not act as a buffer system? Go ahead and give it a try, guys. Okay, so which one will not act as a buffer system? Again, a buffer is going to be a weak acid and its conjugate in the form of a salt. And so in this particular case here, weak acid and its conjugate fluoride in the form of a salt. So this one is a buffer. The next one, ammonia, is a weak base. It's with its conjugate. Its conjugate is ammonium ion in the form of a salt, so that is a buffer. This next one, we have HCl and NaCl. Well, HCl is a strong acid, so that one is looking like it's not going to work out, right? And NaCl, sure, is a salt that contains the conjugate, if you want to call it that, but really this guy has no conjugate because the HCl completely dissociates, so there's no equilibrium here to talk about. So definitely this one is going to be an answer. And just to make sure, the next two, this guy right here, this is nitrous acid, which is a weak acid, with its conjugate, which is the nitrite ion in the form of a salt. And then finally, CH3NH2 is actually a weak base that is structurally very similar to ammonia, but is one where we have replaced one of the hydrogens with a methyl group. Remember that we have already talked several times about this kind of nitrogen bases. Anyways, if this is our weak base, the conjugate of this would be CH3NH with NH3 with a positive charge. And of course, this would need to be found in the form of a salt with a counter ion, which in this case was the chloride ion. And so definitely these two would have also worked as buffers. So that's that. In this slide, I wanted to show you the effect of a buffer. On the left-hand side, I have a buffer system. On the right-hand side, I have just water. They are of the same volume, 1 liter. This one on the left has a buffer that is acetate buffer. Notice that we have acetic acid together with the acetate ion. Both of them are, in this case, at the same exact concentration. And the pH of that solution is 4.74. Here on the right-hand side, I have water, which initially has a pH of 7. I then add the same amount of a strong base to both. On the left, or on both cases, is sodium hydroxide, 5 milliliters, 4 molar. So basically, I'm adding the same number of moles of that base to both systems. And as you can see, for the buffer, the pH barely moves. It goes from a 4.74 to a 4.80, while for the water, the change is significant. We go from a pH of 7 to a pH of 12.3. So the change in pH is 0.06 for the buffer and 5.3 pH units for the water. So obviously here we're showing that the buffer was in fact able to resist changes in pH. But I also want you to notice that it doesn't mean that the pH doesn't change at all. It does change a little bit, and it changes in the direction that we expect. If we add base, we expect that the pH is going to increase, right? But the change is going to be very small. Now, in the next few slides, we're actually going to be learning how to calculate what the new pH will be for that buffer after addition of an acid or a base, and so that you're able to compare it to the unbuffered system.